In lecture number 3, I promised you that this next lecture we talk about numbers that are not rational. What does that mean? Well, we defined a rational number as a number that can be written as the ratio of two integers. So obviously an irrational number is one that cannot be written that way. We need to go back to the 6th century BC. The Pythagoreans believed that all existing numbers, all numbers they knew of at that time and all numbers that existed in the human experience could be represented by a whole number or the ratio of two whole numbers. In an ironic way, the theorem that is named for the Pythagoreans was used to prove that notion that all numbers were rational to be wrong. The Pythagorean theorem states that the sum of the squares of the two legs of a right triangle is equal to the square of the hypotenuse. A squared plus b squared equals c squared. We've all seen that in school. But Aristotle, famous Greek philosopher, Aristotle proposed a square whose side had length n, that is 4 sides of length n, that had a diagonal of length m, where m and n were both counting numbers, and that the ratio of m to n could not be simplified, could not be reduced. That is, m and n shared no common divisor other than 1. Okay, so we have this square. We now, if we talk about the two sides of the square and the diagonal, we have a right triangle. A right triangle whose two legs measure n and n, and whose hypotenuse measures m. Using the Pythagorean theorem, Aristotle showed that m squared equals n squared plus n squared, or m squared equals 2n squared. Next, he showed that m squared must be an even number because it is equal to 2 times the square of n, and n is a counting number, and 2 times any counting number is even. So m must be even and can be written as 2 times h, where h is some counting number. If we squared m, we get m squared, and of course that must be equal to 2h times 2h, or 2h squared, which is 4h squared. So we have m squared equal to 4h squared, and we also have m squared equals to 2n squared. And we can replace the m squared and get that n squared is equal to 2h squared. That is, 2n squared equals 4h squared, dividing both sides by 2. N squared must equal 2h squared. This means that n is an even number. Actually, it means that n squared is an even number, and therefore n must be an even number too, because you cannot square an odd number and get an even number. Okay, so we have n is an even number, m was an even number. This is a contradiction, because remember we said that the two numbers m and n share no common divisor other than 1, but if they're both even numbers, they share the common divisor of 2. And the contradiction means that something is wrong. And the only thing to be wrong is the original supposition that m over n was a rational number. That is, m and n are two whole numbers, and therefore the ratio is a nice fraction. This is not true. So Aristotle used the Pythagorean theorem to show that indeed there were numbers that were not rational. And in fact, they're called irrational. Once we understand that irrational numbers exist, we can begin to look at the various types of rational numbers. A common type of rational number is the square root of a number that is not squared. It is interesting to note that from 1 through 10,000, there are only 100 square numbers. That is, 1 squared is 1, 2 squared is 4, up to 100 squared, which is 10,000. From 10,001 to 40,000, there are only 100 square numbers. That's 101 squared through 200 squared. So there are 29,900 numbers from 10,001 to 40,000 that are not square, and their square roots are rational. The number of counting numbers that are not square far exceeds the number of square counting numbers. Thus, there are a large number of irrationals that are equal to the square roots of these non-square or unsquare counting numbers. One interesting pattern that exists when looking at the square roots of numbers is that the digits in the ones place of a square number can be looked at and something about its square root is known. It is impossible to multiply a digit by itself and obtain a number that ends in 2, 3, 7, or 8. Which means if we have a number, a counting number that ends in 2, 3, 7, or 8, I don't care how small or how large it is, its square root is not a whole number and must be irrational. So there is no square number that ends in 2, 3, 7, or 8. Looking at the square root of 2, we can know that it must be more than 1, since 1 times 1 is 1. It must be less than 2, since 2 times 2 is 4. If it is rational, and it is not a whole number, because there is no whole number between 1 and 2, then it can be written as a decimal at 1 point something, 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 etc. And we multiply 1 point something, 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 times itself, we better get 2.0000, etc. Now, that means the last digit in our decimal rational number, that's the square root of 2, multiplied by itself, multiplied by that same digit, must be 0. What digit do you know when multiplied by itself gives us 0? The only one I know of the 10 digits is 0, but it can't be 0 because if it's 0, we don't need it. And we proceed to the next place, and the same rationale leads us to the fact that the square root of 2, if it is a rational number, must be 1. But 1 times 1 is not 2, and therefore the square root of 2 is not rational. 0, therefore, is a key. And again, remember that we talked about that people didn't understand that 0 was an amount. And we know, therefore, by our modern use of decimal numbers, that the square root of 2 cannot be a whole number, it cannot be a fraction, therefore it cannot be a rational number, and therefore it is irrational. Other types of irrationals are found by taking the roots beyond the square root, the cube root, the fourth root, etc. It takes 10,000 counting numbers to get the first 100 square numbers. It takes 1 million counting numbers, from 1 to 1,000,000, to get the first 100 cubic numbers. Thus, in the first 1 million counting numbers, there are 999,900 numbers, counting numbers, that do not have a rational cube root. And there are even more irrationals created by taking the fourth root of a number. And again, as we increase the number of the root, the fifth root, sixth root, it takes more and more counting numbers just to get a few that work, and therefore we're going to wind up with tons of irrational numbers. Are those the only irrational numbers out there, these cube roots and square roots? Not at all. As humans began investigating the application of mathematics, important irrational numbers were discovered. Probably the first one was the universal ratio between the circumference and the diameter of a circle. The natural base for many exponential functions is also an irrational number that became very, very important as mathematics developed in Europe during the 17th and 18th centuries. The use of irrational numbers led to development of some very common mathematical symbols, symbols we see and use regularly, especially in mathematics class. Prior to the 16th century, mathematics problems were written with words. There were no symbols involved other than possibly the numerals. If you wanted to add a number to 3 to get 5, you would say, what number must I add to 3 to get 5? That number is 2. But as the use of mathematics became more important in applications in various areas, there was a need to simplify the writing of these kind of problems. And symbols developed. The first symbols were abbreviations. And from those abbreviations, in many cases, came the symbols we use today. The plus, the minus. Okay? The Latin word for root is radix. And remember, most of the great work in mathematics and science, in fact, most of the educational work done in medieval Europe and even into 18th century was written in Latin. That was the language of scholars. So we have this word radix, which means root. And the abbreviation of radix was the beginning of the creation of the symbol we now use as the square root. For example, we had the first symbol was a symbol that R combined with an X, similar to the prescription symbol we recognize in pharmacies today. And that was a symbol for the radix, or the root, the square root. Then this was replaced with a check mark, and sometimes a 2 was used to represent the square root. Since the square root was most common, the 2 was removed, and in 1525 the check mark came about as to be fairly common. In 1553, the symbol was changed to to make it look like a small z with an extension. And finally, in the 1600s, the radical symbol, which we use today, was in common use. This was based on a fancy version of the letter R in radix. So again, we started with radix and we went to this RX kind of thing, and then they tried various other situations and settled on a fancy version of the R in radix, and that's the square root used today. And again, in square root, we don't put a 2. All other roots, which are far less common than square roots, we see a 3 for a cube root and a 4 for a fourth root, etc. Let's talk about the ratio between the circumference and the diameter of a circle. This was a number that was sought after as soon as people began using circles, which goes back to ancient times. The Babylonians, one of the earliest users of mathematics, thought the ratio was approximately 3 1/8. This was in 1700 BC. In the Old Testament, in 1 Kings 7:23, while describing King Solomon's temple, which is 1000 BC, the ratio is indicated to be equal to 3. There's been some research to show that there were 2 different Hebrew spellings of the word for linear measurement in that portion of the Old Testament. And since, remember, we said that Hebrew, the letters were also numerals, if you take the ratio of those 2 numbers, the larger number over the small, that is, the numbers indicated by the different spellings of that word, take that ratio and multiply it by 3, we get a fairly accurate approximation of the ratio, the common ratio between the circumference and the diameter of a circle. So perhaps the writers of the Old Testament knew more mathematics than we give them credit for. In the 3rd century BC, Archimedes believed that the ratio was between 3 1/70 and 3 1/7. Archimedes is one of my heroes. Archimedes was a genius beyond mathematics. He was the Ben Franklin, I guess, of his time. He not only was a great mathematician and scientist, he also was a designer of military tools and a great thinker. But to me, what he did, and how did he do this, coming up with something between 3 1/70 and 3 1/7, which of course is accurate. He would take circles and he would take triangles, squares, and other polygon shapes and inscribe them inside the circle and inscribe the circle inside one of the same shape. And keep looking at the areas and the ratios and basically, of course, again, there was no television, no radio. He had nothing better to do, so he spent his time doing this and came up with a very close approximation, given the tools that he had to use, to what this actual ratio is. In China, in the year 470 AD, the ratio was written as 355 over 113. This translates as a decimal to 3.1415929 and so on, which is very close to the number we believe today is the true ratio. 40 years later in India, the ratio was written, and here's an interesting number, 62,832 divided by 20,000, which of course is 3.1416. So very, very accurate to the 10,000th place. Now, again, what kind of life did the person lead who spent time figuring out that ratio? I'm not sure, but he probably had nothing much else to do. Some years later, in 1736, Leonhard Euler, a Swiss mathematician, first used the Greek letter pi to symbolize that ratio. And Euler was so respected in his writings that when he started using the symbol pi, the Greek letter pi, everyone immediately accepted it And since then, this has been the symbol we've used for that common ratio between the circumference and the diameter of a circle. Okay? Pi is an irrational number, since this decimal representation neither terminates nor has a repeating cycle. It is irrational. The digits in pi have no pattern and have been used to create random numbers, something we'll talk about in probability later on. But the idea is you cannot predict what the next digit will be in pi unless you've memorized, and some people have done that too, memorized hundreds of digits of pi. I remember as a child watching a science fiction movie back in the 50s where pi was used to communicate with Martians, or supposed Martians. The use of pi was suggested since any culture with advanced science would be familiar with the ratio. And if I remember correctly, they sent radio beeps, 3 beeps, and then 1 beep, and then 4, and it was answered 3, 1, 4, 1, and so on and so forth. And from that beginning, there was communication. And I haven't seen the movie on TV in about 40 years, but it's probably out there someplace. Very interesting. And the whole situation came when the scientist hero saw the young boy eating some pie and said, of course, pie. These Martians would know about pie. Very, very fascinating. As application of mathematics became more complex, exponential forms of numbers became very useful. The discovery of a base that was found in various exponential settings required a symbol. This natural base was first recognized in 1618 by John Napier. Napier is given credit for the development of tables of logarithms, and eventually that led to the use of the slide rule, which those of us who probably passed 35 or 40 may remember engineering students carrying around on college campuses. That slide rule has gone into along with the vacuum tubes today because of the calculator and the computer. In 1728, 110 years after Napier, Euler suggested that this natural base be called E. I believe, and I've read, that E was for exponential, but eventually people became convinced that E was for Euler. That is, not Euler picked it himself, but people used E to honor Euler because of his work with exponentials. And he defined this E as the sum of 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus 1 over 1 times 2 times 3 times 4 ad infinitum. And this can be written symbolically as the limit, that is, what's happening, where it's going, as n goes to infinity, of 1 plus 1 over n, all raised to the nth power. Now, as n gets larger and larger, 1 plus 1 over n is closer and closer to 1, but it's never exactly 1. It's just a little bit more than 1. And as n gets larger, we're raising this number that's just a bit more than 1 to a very high power. And that is how Euler defined E. The decimal representation of E, by the way, is 2.718281, and it does not terminate, and it does not have a repeating cycle. So E, this natural base for exponential numbers, is an irrational number. Euler combined the most significant symbols in mathematics in one equation. E to the I pi power plus 1 equals 0. The I is the square root of negative 1, something we will discuss at length in the next lecture. And notice, these are the 5 important numbers. E, the natural base, I, the square root of negative 1, pi, the ratio of the circumference to the diameter of a circle, 1, the creator number, and 0, the number for nothing. And Euler is credited with proving that this was true. The use of common square roots required the development of rules for operating with these numbers. Because no longer were we just concerned, is the square root of 5 rational or irrational? We were concerned about doing arithmetic with the square root of 5. And again, the rules for using these square root numbers are the same as the rules for whole numbers. They appear to be different to people, but in general, we think about that addition and subtraction. We must add numbers with the same place value. If you look at the square root of a number as its place value, so that the square root of 2 is the place value. We can have 1 square root of 2, we can have 2, we can have 7 square root of 2s, but the square root of 2 is place value. And the square root of 2 plus the square root of 3 cannot be added. The answer is the square root of 2 plus the square root of 3. Since we have two different place values, we can only add or subtract numbers that have the same square root and therefore the same place value. If, for example, we wanted to add the square root of 8 plus the square root of 2, at first glance you say, wait a second, we can't do this because the square root of 8 is not the same place value as the square root of 2. But we do know that 8 has a factor of 4, and the square root of 4 is a nice whole number. So we can take the square root of 8 and translate it as the square root of 4 times the square root of 2. And the square root of 4 is 2, so therefore the square root of 8 becomes 2 times the square root of 2. And of course we now have 2 times the square root of 2 added to 1 times the square root of 2. The 1 is not shown, but we know if it says the square root of 2 means one of them. And 2 plus 1 is 3. 2 of anything plus 1 of the same thing is 3 of that. So 2 square root of 2's plus 1 more square root of 2, the answer is 3 times the square root of 2. Therefore the square root of 8 plus the square root of 2 is equal to 3 times the square root of 2. Subtraction is accomplished in the same way. We can take a look at the square root of 50 minus the square root of 18. And at first glance, you say, well, I can't do that because we have 50 and 18, and I'm not sure how we can possibly subtract those. And in reality, the question we've got to ask is there a number that we can divide into 50 that's a square number? So we can take the square root of that number, and what's left inside that square root is the same as if we do the same thing to 18. And of course, the answer is yes. 50 can be divided by 25. 25 times 2. And the square root of 50, therefore, is the square root of 25 times the square root of 2, and the square root of 25 is 5. So the square root of 50 can be written as 5 times the square root of 2. Similarly, the square root of 18 is equal to the square root of 9 times the square root of 2, which is 3 times the square root of 2. So our problem now is 5 times the square root of 2 minus 3 times the square root of 2, which of course is 2 times the square root of 2. We were able to subtract because we were able to translate our problem into two numbers that had the same square root, the same place value. How about multiplication? Well, when we multiply, remember we multiplied each digit in each number by every digit in the other number. And when we multiplied digit times digit and place value times place value. We do the same thing here, except now the place value is the square root, and the digit could be 1 if we have the square root of 5, that's 1 square root of 5. We also could have 2 times the square root of 5, or 8 times the square root of 5. Okay? If we wanted to multiply the square root of 3 times the square root of 7, we could do that. The square root of 3 times the square root of 7. In effect, we have 1 square root of 3 times 1 square root of 7, and that would be 1 times the square root of 21. 1 times 1 is 1, and the square root of 3 times the square root of 7, we multiply place values, we get the square root of 21. So the square root of 3 times the square root of 7 is the square root of 21. Next, let's take a look at the multiplication of 3 times the square root of 6 multiplied by 2 times the square root of 2. Again, we multiply the numbers out front, what I call the digits, the 3 and the 2, to get 6. And we multiply the place values, the square root of 6 times the square root of 2, to get the square root of 12. So our answer appears to be 6 times the square root of 12. But we're not finished yet. 6 times the square root of 12 can be simplified because 12 has a factor of 4. So we can write 6 times the square root of 12 as 6 times the square root of 4 times the square root of 3. And the square root of 4, of course, is 2, and 6 times 2 is 12, and we wind up with 12 times the square root of 3. So 3 times the square root of 6 times 2 times the square root of 2 is 12 times the square root of 3. It is noted that if you multiply a square root by itself, you get a rational number. That is, the square root of 3 times the square root of 3 would be 3. Even though the square root of 3 is irrational, multiplying that square root by itself gives us a rational number. Now, how could we take an irrational number and multiply it by something other than its square root and get a rational number. Well, let's take a two-term irrational number. In some places, this is called a surd, S-U-R-D. A surd is simply an irrational number. In many cases, it contains two parts, one of which must be irrational. So we have the square root of 5 plus the square root of 2. That is a surd. The square root of 5 plus 3 would also be a surd. And we're looking at multiplying the square root of 5 plus the square root of 2 by something that will give us a rational number. What was discovered was if you take that square root of 5 and that square root of 2 and replace the plus in between them with a minus, that is, you get an irrational number that looks identical except for the sign in between the two irrational parts. And you multiply, in this case, the square root of 5 plus the square root of 2 times the square root of 5 minus the square root of 2. You wind up with a rational number. Let's walk through it. Remember, we're going to multiply each part of the first number by each part of the second number. Multiplying the square root of 5 times the square root of 5, we wind up with 5. Multiplying the square root of 5 times negative the square root of 2, we get negative the square root of 10. Again, we multiply the square root of 5 times the square root of 2. When we multiply the square root of 2 in the first number by the square root of 5 in the second number, we get plus the square root of 10. And the square root of 2 times negative the square root of 2 is minus 2. The negative square root of 10 and the positive square root of 10 cancel out. We're left with 5 minus 2, which is 3. So we took an irrational number, the square root of 5 plus the square root of 2, multiplied it by another irrational number, and got a rational number. We can do this. And when you have numbers of this type, where you have two terms, at least one of which is a square root, you can multiply it by its conjugate. That is, a two-term irrational number where everything's the same except if it was a plus in the first number, you put a minus in the second. If there had been a minus in the first number, would have put a plus in the second. Multiplying those two numbers, multiplying a number times its conjugate, will give you a rational number. How about dividing? Here is a division problem. The square root of 2 divided by the square root of 5 plus the square root of 2. You might say the answer to this is, who cares? But there's got to be a way to do this. And someone came along, and rather than trying to figure out how to divide by a complex number like the square root of 5 plus the square root of 2, someone, and I really don't know who that person was, said one day, look, we know if we multiply the denominator by its conjugate, we will have a rational denominator. And we don't care what we have in the numerator, whether it be rational or irrational, we certainly can then write that number as the numerator over whatever the denominator is as a rational number. So we multiply the top and bottom of the fraction by the conjugate of the denominator. We multiply by the square root of 5 minus the square root of 2, top and bottom. The square root of 2 times the square root of 5 gives us the square root of 10. The square root of 2 times negative the square root of 2 gives us minus 2. So the numerator of our answer fraction is the square root of 10 minus 2. We cannot simplify that. But the denominator, because we're multiplying a number by its conjugate, we wind up with a rational number. We already saw that the square root of 5 plus the square root of 2 multiplied by its conjugate gives us a rational number. It gives us 3. So our answer to what is the square root of 2 divided by the square root of 5 plus the square root of 2 is the square root of 10 minus 2 all over 3. And you might say, gee whiz, when are we going to use this? Well, the notion is in the real world there are things that are irrational. In practical situations, we may want to take, for example, the square root of 2 and call it 1.4, because certainly 1.4 times 1.4 is very close to 2. But in some situations where precision is necessary, we'd like to be able to use irrational numbers. And now, at least on a cursory level, we can add, subtract, multiply, and divide irrational numbers. Again, you can take a whole course on this. The purpose of this lecture was simply to introduce you to the notion and the creation and the workings of irrational numbers. In our next lecture, lecture number 5, we'll go beyond the irrationals and talk about the imaginary and the complex. And you say, how can we talk about imaginaries? If they're imaginary, wait and find out.